Okay, so question 2 is talking about the mean value theorem. I'll just briefly go over what the mean value theorem is. Mean value theorem says, suppose I have a function that's defined from A to B, right? So I'm just going to randomly make up some function here. Let's say it looks like this. Notice the closed interval. That means we have to include A, we have to include B. If these are not included, the mean value does not apply, right? For example, if they said like this, the mean value theorem wouldn't apply, right? Remember, this sideways bracket means A is not included, so the side points have to be included. What it's saying is if I find f of b minus f of a over b minus a, which is the slope of the secant line, right? So if I find the slope of this line here, this is the slope of the secant line, then there exists some point in between a and b. We're going to call it c. There's just some x value in here where the slope of the tangent line is the same, right? So it's saying in between there's some tangent line that's the same slope as the secant line that goes through f of a and f of b, right? So in general, what you have to do is you have to find the slope of the secant line, set it equal to the derivative of the function, and find x, or this c value, right? What is the x value that produces this slope? All right, so in this case, our function is g of x equals x cosine squared of x. A is 0, b is 5 pi, and we want to find the values of c. What is the c value where the secant line, the slope of the secant line is equal to the slope of the tangent line. So let's find the slope of the secant line first, right? F of b minus f of a over b minus a. This should equal f prime of c. Remember, c is between a and b, right? So we're finding this, so that's going to be f of 5 pi. Our function is called g, so I'm just going to put a g here. G of 5 pi minus g of 0 over 5 pi minus 0. So g of 5 pi is 5 pi times cosine of the square root of 5 pi minus g of 0 is just going to be 0, right? If you plug in 0 there, you're going to get 0. That's all over 5 pi. All right, so the left-hand side of this equation that I have here is basically the slope of the secant line. Remember, and actually these will cancel. And so we're left with cosine of square root of 5 pi equals f prime of c. All right, so again, this is the slope of the secant line. This is the slope of the tangent line. In order to find the slope of a tangent line, we need the derivative, right? So let's go back up here. Our function g of x is x cosine square root of x. To find the derivative, we're going to need product rule, which is going to be derivative of the first times the second, plus derivative of the second, which is negative sine square root of x times the derivative. This requires chain rule. Derivative square root of x is 1 over 2 square root of x, right? And then times the first function. If you simplify this, simplify this out a little bit, and we get cosine square root of x minus sine square root of x times square root of x on the top over 2. That's g prime of x. And so what this function, so that's f prime of c. So we end up with cosine square root of 5 pi equals cosine square root of, and actually I'm going to go and replace this with c now because it's some c value, which is the x value also. You can leave it as x if it makes more sense to you. All right, we're trying to solve for c. And you are allowed your calculator on topic 9, the third test. So probably the easiest way to solve this is using your calculator. I'll show you the way you can do it. The way I would do this is go ahead and graph both of these these functions. So graph cosine of square root of x minus sine square root of x times the square root of x in parentheses here, and then this whole thing is divided by 2, which is the same thing as multiplying by half, so I'm just going to do it that way, even though it doesn't look quite the same. And then here we're going to do cosine of the square root of 5 pi, right? And we're going to go to graph both of these. We might need to adjust our window. So the first one being graphed should be the first equation I entered, which is this one. And the second one should be the second equation I entered, which should be a constant straight line. And it looks like this. Notice that we see a point of intersection twice, which means there might be 2 solutions to this. So I'm going to go ahead and change my window so I can see this function better. We don't really need to see that many negative x values. We need to see further on this. We actually need to see all the way to 5 pi, because that was our b value, right? That was on our interval. So instead of going to 5 pi, I'm going to go to 6 pi, a little bit beyond 5 pi. And then we don't really need to see very high or low on the y-axis. I'm going to go from -2 to 2. And this should give me a much better graph. So there's the first one, there's the second one, and we see how there's 2 points of intersection. We're going to use our calculator to find those points of intersection, and the x values there will give us our c values. So we're going to say second trace intersect, which is number 5. It's just going to ask first curve. You just need to make sure you're on the curvy one. Second curve, make sure you're on the line. Guess is where you need to get close to the point of intersection you actually want to find. Let's find the lower one first. So let's go close to this point of intersection and then press enter. And you can see that x value is 2.2569. So one of these c values is going to be 2.27, right? 3 significant figures since it didn't specify. We're going to find the other one, second trace. What's going on in second? Here it is. Intersect. Again, it's going to say first curve, second curve. Guess you got to get over next to this one. Since we want to find this point of intersection now, press enter. And the other c value we're going to get is 11.1 to 3 significant figures. Right, so there's actually 2 values here where the tangent line has the same slope as the secant line. And we'll see graphically what this looks like on part 2b. Right, so part 2b says, sketch the graph of y equals g of x on the interval from 0 to 5 pi. Let's go ahead and just get a graph of this going here. G of x was x cosine square root of x so let's see, I probably need to change this now. I need to change my window to actually see this function better. You can see it goes way down there, so window, we need to see further down, so let's make this negative, I'm not sure how far down we need to go, -10. We need to go down even further than that. See, it comes back up here. Maybe negative. Let's try -15. See if that's far enough down. Okay, cool. So there it is. So when we are asked to sketch a graph, we need to provide a general shape and like important points, right? So if we're going to sketch this, we for sure need axis intercepts, right? So the way you can find axis intercepts here, if you want the y-intercept, second trace, second, oh no, what happened to my, I don't know what happened to this thing. Okay, so second trace. If we want the y-intercept, we just need a value. When x is 0, that will give you a y-intercept. At 0, it's 0, so we know there's a y-intercept at 0. So we can go ahead and mark that at 0, 0. We need an x-intercept, which we're going to find by doing second trace number 2. Option 2 is 0. For this, you need to go left bound, which means you just need to make sure your cursor is left of the 0. And then right bound, you need to make sure your cursor is right of the 0. And then guess is you just get close to the x-intercept you're trying to find and guess, press enter. The x-intercept occurs at 2.467. So we'll make a little mark here. This, and that's our x-intercept. You can see the function comes up and back down. And this is 2.470 x-intercept, right? We have to label our axis intercepts. And then our function goes down and comes back up. We only need to do this until 5 pi. So let's go ahead and get our value at 5 pi, right? Because that's our interval. So we're doing second trace value at 5 pi. At 5 pi, we have -10. So let's say this is 5 pi, then my y value down here is going to be, actually, let's put -10 here, there, and you can see general shape from there is it, has a relative minimum down there and then comes back up. So that's the general shape of this graph. When we found this left-hand side of this equation, that was the slope with a secant line, right? So that was, let me do this in a different color. That was the slope of the line connecting g of 0 and g of 5 pi, right? So if I connect those two, again, I'm doing this on a computer, it's kind of difficult. You should do it with a ruler, a straight edge, right? This is the secant line. We found the slope of that secant line. And then we found that the slope of the tangent line is equal to the slope of the secant line when c equals 2.27. So 2.27 somewhere before before that x-intercept. The slope of that secant line is the same as the slope of the tangent line, and it's equals 11.1, which is somewhere over here. You can kind of tell based on the function where it's going to be. Then that is also there. Basically, the slopes are the same, they're parallel, right? So we should be drawing 3 parallel lines here. Let's see what else is asked for. Illustrate the mean value theorem for the function, right? So we're just creating a graph of this. I'm going to do this on Desmos as well so you can see a better picture of what it looks like. Okay, so here's g of x, x squared root of cosine x. We could find the slope of the secant line by doing g of 5 pi minus g of 0 over 5 pi minus 0, which is that. So the slope of the secant line is -6.8, which is what we had up there as well. Then what you can see is that if you do g prime of what we said, 2.27, which we said where the slope of this tangent line should be the same, you can see you also get a similar number, right? Rounded slightly differently, just because we rounded our c value. And also we do g prime of 11.1, we also get a very similar, basically the same slope. Again, this is because we kind of rounded these numbers off a little bit. that they're not perfectly the same. And so what we're saying is if I drew the secant line through this point, let me go ahead and call this a number. Let's call this m. If I wrote this equation of the secant line, which is y minus 0 equals m x minus 0, that's the equation of the secant line. If I wrote the equation of the tangent line, then it would be y minus the y value, which is g of 2.27 equals g prime of 2.27 times x minus 2.27. It creates that secant line that you can see, or that tangent line. You can see it's tangent to the function here at the value 2.27, and it's parallel to the secant line, right? The slope is the same. And we could also do the same thing for the 11.1, right? So g of 11.1, that gives me the y value equals g prime of 11.1. That tells me the slope, x minus 11.1. And here's the other tangent line that is parallel to that secant line, right? Notice both of these occurred within the interval, right? Within the interval from 0 to 5 pi, the two tangent lines. And so this is the graph should look something like this on your paper, right? Okay, hopefully this is helpful. Keep watching the other videos to get more help.